We have the question on today's document about the equipotential surfaces for the field that we found previously in the last class. Remember that we had a charge Q at the origin, and we found the electric field using Coulomb's law essentially, and we found the potential function, which is just KQ over R, at the point x, y, z. Now, at the point x, y, z, R is just the square root of x squared plus y squared plus z squared, just the Pythagorean theorem. So we have this potential function, and we took the gradient of this potential function and found out that that was equal to the electric field, as it must be for the conservative field. If this is a potential function for the conservative electric field, then its gradient is equal to the electric field. Okay, so anyhow, an equipotential surface. Equipotential implies that the potential function is constant. So we could have written v of x, y, z equals constant, but that's implicit. So setting this potential function equal to a constant, we easily rearrange this equation. We could write this equation kq over square root of x squared plus y squared plus z squared minus the constant equals 0. So we know that this is a surface because, in general, for a continuous function f of x, y, z, f of x, y, z equals 0 gives us a surface in three-dimensional space. And we want to identify that surface. Well, this doesn't look exactly like any surface that we're familiar with, but it turns out to be one of the simplest quadric surfaces. So if we rearrange it, just put the x, y, z squared over here and square both sides, we get this, and this is very straightforward. And then we can solve and isolate x squared plus y squared plus z squared, which is kq over constant squared. And that's of the form f of x, y, z. Well, it's not quite of the form f of x, y, z equals 0. It would be if we subtracted this from both sides. However, we're going to keep it in this form because we know that then, if we remember anything about quadric surfaces, this is the simplest type of quadric surface, basically, that x squared plus y squared plus z squared, all having the same coefficient equal to some constant, means that we have a sphere. We should immediately recognize this, but maybe we're a little rusty. Remember that the equation of a sphere is x minus h squared plus y minus k squared plus z minus m quantity squared equals r squared. The center of this sphere is hkm. Its radius is r. Well, that means that here we have a sphere, center 0, 0, 0, because this is x minus 0 squared, y minus 0 squared, z minus 0 squared. And the radius is, well, the square root of this. This is r squared, so r is just our kq over constant. And I guess the one thing I should do to make this a little more correct is it's the magnitude of kq over constant, because, of course, q could be negative. Okay, well, in any case, that's our equipotential surface.